Hello everyone and welcome to my video seminar on power control, scheduling and interference management. My name is Salman and I'm a PhD student at Network System Lab at Inha University. I have prepared an additional slide with the recommended slide, so I'll be switching back and forth to these two slides. And this one slide I have elaborated some terms and more detail. We will see the abstract view of the presentation in these slides, and then for further detail I'll refer to this one slide. I'll start with a very generic scenario of the uplink power control. Let's assume an example. You just turn over your mobile phone, and the mobile phone, which is transmitting in this case, has to send some signal to the base station, which is here. How strong power the mobile phone has to transmit. This is very important. If the mobile phone is transmitting the signal in too low power, the base station would not detect it. And if it transmitted in too high power, it can interfere with the communication between the mobile phones or the neighboring cells. So it has to determine the proper power transmit level, which would be strong enough to be properly decoded by the base station and weak enough not to interfere in the communication between the other mobile phone that is belonging to the neighboring cells. How do we handle this situation? What kind of method the user equipment should use to determine the proper transmission power? So to start our lecture, we have to cover a couple of topics like the uplink power control, scheduling and rate adoption, inter-cell interference coordination, and heterogeneous network deployment. So we will see all these one by one. For the uplink power control, let me show you first the big picture of the open loop power control and the closed loop power control. There are roughly two different ways of power control mechanism. One is called open loop power control and the other one is called the closed loop power control. When we say open loop power control, it does not mean loop control. It is just one direction control process. There is no feedback as illustrated in this figure. Actually, a control path that does not have any feedback input in the definition of open loop in control theory. An open loop control user equipment determines a transmission power by its own power setting algorithm. And all the power setting algorithms are coming from an algorithm which is defined here. For example, the path loss and from the higher layer signaling or other effects. And based on these, the algorithm will decide how to adjust the power of the user equipment. This power setting algorithm takes many inputs, but all of these inputs are from the user equipment internal settings or measurement data by the UE. There is no feedback coming from the base station. One of the most common example of open loop power control is the physical random access channel, or we also call PRAC. Conversely, we have the closed loop power control. It means that the user equipment is getting some feedback from the base station. So the base station is sending some instruction in the form of transmission power control decision algorithm, and the transmission power control decision algorithm basically takes the target SINR and the measured SINR, and basically the difference between the target and the measured SINR, it just adjusts it and then send the feedback through the transmission power control to the user equipment, and the user equipment then adjusts at power according to the instruction coming from the base station, and finally it sends the data or control signal to the base station based on that power. So what are the uplink power control basic rules? The uplink power control basic rules are following. With the LTE release 10, there is a possibility for the carrier aggregation, implying that multiple PUSCH may be transmitted in parallel on different component carriers. With LTE release 10, there is also the possibility of simultaneously PUSCH or PUCCH transmission on the same or different component carriers. In principle, each physical channel is separated and independently power controlled. However, in case of multiple physical channels to be transmitted in parallel from the terminal, the total power to be transmitted for all physical channels in some cases may exceed the maximum terminal output power, which we denote by PT max, corresponding to the terminal power class. So the basic strategy is to first ensure the transmission is assigned the power assumed to be needed for reliable communication. This means The remaining power available is then assigned to the remaining physical channels. So the total transmission power for the given component carrier should be less than or equal to the PC max of the carrier. This P subscript C max C basically denotes the power control limit of the physical channel. However, separate power control algorithm does not ensure the total transmit power for all the component carrier to be transmitted by the terminal is less than or equal to the PT max. But power scaling applied to the physical channel, however, ensures this constraint for the PT max. Therefore, the power control is carried out in such a way that the control signaling on each layer, for example, layer 1 and layer 2, is given high priority than the data transmission. So for the PUSCH power scaling, it is denoted by this equation where the WC is the power scaling factor for the PUSCH and the carrier C. And this term is basically denoting the transmit power for the PUSCH and carrier C by algorithm. However, this is before power scaling, but it has to include the PC max limitation too. Then the P subscript PUCCH is the transmission for the PUCCH, and the PT max, as we saw earlier, is the output terminal power. So this is a kind of constraint here on the PUSCH power scaling. For PUCCH, the appropriate received power is simply the power needed to achieve a desired, that is sufficiently low error rate in a decoding of L1 and L2 control information transmitted on PUCCH. However, it is important to bear two things in mind. Firstly, in general, the decoding performance is not determined by the received signal strength, but rather by the received signal to interference plus noise ratio, which we call SINR. And it is appropriate received power, thus depending on the reference level at the received side. An interference level that may be different between the different deployments, which may also vary in time, as for example, the load of the network varies. And secondly, given a subframe, UE wants to transmit the PUCCH. This PUCCH has different format which carries different L1, L2 control information such as HERQX, scheduling request, and channel reports, etc. etc. Different PUCCH may carry different info bits per frame, and hence it can have different error rates. That is the reason the SINR might be different for different format of PUCCH. So the overall power control for the PUCCH is given by this expression. And this expression, this term, the P subscript PUCCH, is the transmit power to use in a given subframe, and the PL subscript DL is the downlink path loss as estimation by the terminal. The minimum P subscript C max, comma C, this term ensures that the PUCCH transmit power as determined by the power control will not exceed the per carrier maximum power, which is the PC max, comma C. This delta format is the offset for remaining format configuration by the network, and this delta is a very important term, and it's basically denotes for the network to directly adjust the PUCCH transmit power by explicit power control command, which means each received power control command increase or decrease the term delta by certain amount. All these details you can read in this one slide. And further looking for the power control for the PUSCH, this was the power control for the PUCCH, and this one is the power control for the PUCCH. Power control for the PUSCH can be described by this expression. Here the M denotes the instantaneous PUSCH bandwidth measured in number of resource blocks, and the terms delta MCS is almost similar to the delta format that we saw in the power of PUCCH, and it reflects the fact that different SINR which is required for different modulation schemes and coding rates used for the PUSCH transmission. This expression is clearly similar to the expression for the PUCCH as we saw above, but there are some key differences, and the key differences are, for example, this term P subscript C max, comma C minus PUCCH, it reflects the fact that the transmit power available for the PUCCH on a carrier is the maximum allowed per carrier transmit power after the power has been assigned to any PUCCH transmission on that carrier. This ensures that the L1, L2 signaling and the PUCCH were data transmission are PUSCH in the power assignment. The next difference is this term, which is the 10 log 10 of M, which reflect the fact that what is fundamental controlled by the parameter P0, PUSCH. And this one is the power per resource block for a large resource assignment. A correspondingly higher received power and this correspondingly higher transmit power is needed. You can also see this alpha term, which can take the value smaller or equal to 1, which depicts the partial path loss compensation. Assuming alpha equal to 1 operates as full path loss compensation, the PUSCH power control expression becomes very similar to the corresponding expression for the PUCCH. Thus, the network can select a modulation and coding scheme, which we call MCS, and the power control mechanism, including the term delta MCS, which ensures that the SINR will meet the SINR requirement for the MCS scheme. However, with the alpha less than 1, PUSCH power control operates with so-called partial path loss compensation. That is, an increase in the path loss is not fully compensated for by a corresponding increase in the uplink transmission power. In that case, the received power and thus the received SINR per resource block will vary with the path loss, and consequently, the scheduled modulation and coding scheme should vary accordingly. The alpha variation is shown in these two figures. You can see this one is the transmit power and here it is the received power. The solid line, it shows the for the full compensation, which is alpha is equal to 1, and the dashed blue line, it is showing the partial compensation where it is sit in point 8 in this example. As can be seen, the partial path loss compensation, the terminal transmit power increases more slowly than the increase in the path loss. Consequently, the received power and thus the received SINR is reduced as the path loss increases. To compensate for this, the MCS scheme or the modulation and coding scheme, which is the PUSCH data rate, should be reduced as the path loss increases. The power control for the SRS, and this is almost similar to the power control of the PUSCH.C, where the PSRS is the configurable power offset. The parameter P0, PUSCH, alpha, and delta are the same as we saw here in the above equation, which was for the PUSCH.C. Furthermore, the SRS is the bandwidth expressed as the number of resource blocks of the SRS transmission, and the PSRS is the configurable offset. To assess the scheduler in the selection of combination of MCS and size of M that does not lead to the terminal being powered limited, the terminal can be configured to provide regular power headroom reports on its average usage. There are two different types of the power headroom reports defined in the LTE Release 10, which reflects the power headroom assuming the PUSCH only transmission on the carrier, while the Type 2 reports assuming combined PUSCH and also the PUCCH transmission. Dynamic scheduling. So the purpose of the scheduler is to determine which terminal to transmit data on from which set of resource blocks. Dynamic scheduling, where the network in each 1 millisecond transmit time interval transmits scheduling information to select the set of terminals and hence controlling the uplink and downlink transmission activity. These scheduling decisions are transmitted on PDCCHs. To reduce the control signaling overhead, there is also possibility of semi-persistent scheduling. However, semi-persistent scheduling is only supported on primary component carriers, motivated by the fact that the main usage for smart payloads not requiring multiple component carriers. For carrier aggregation, each component carrier is independently scheduled with the individual scheduling assignment or grants and on DLSCH or ULSCH per scheduling component carrier. It will be clear from these two figures. This is the downlink scheduler and this one is the uplink scheduler. The downlink scheduler is responsible for dynamically controlling the terminals to transmit to, and for each of these transmit the set of resource blocks upon which the terminals DLSCH is transmitted. The transport format selections such as the type of block selection and modulation coding schemes resource block allocation, and antenna mapping, etc. for each of the component carrier, and the logical channel multiplexing for the downlink transmission are controlled by the E node B. The uplink scheduler serves a similar purpose, namely dynamically controlling which terminal are to transmit on their ULACH and on which uplink resources, which means in UL scheduler, UE controls the transport format and the logical channel multiplexing. Let's discuss the downlink and uplink scheduler in more details. The scheduler is in control of instantaneous data rate used, and the RLC segmentation and MAC multiplexing will therefore be affected by the scheduling decision. Although formatting part of the MAC layer to some extent viewed as a separate entity, the scheduling is thus controlled most of the functions in the E node B associated with the downlink transmission. The first one is radio link control. Depending upon the level of the data, the radio link control service data unit is chosen. For low data rates, it may only be possible to deliver a part of RLC SDU in the TTI, in which case segmentation is needed. Similarly, for high data rates, multiple RLC SDU may be needed to be concatenated in a sufficient large transport block. The second important thing is MAC. The multiplexing of logical channel depending on the priority between different streams. For example, the radio resource control signaling, such as the handover commands, typically has a higher priority than the streaming data, which in turn has higher priority than a background file transfer. Thus, depending on the data rate and the amount of traffic of different priorities, the multiplexing of different logical channel is affected. But please remember that hybrid ARQ transmission is also needed to be accounted for. And finally, the L1 coding modulation, and if applicable, the number of transmission layer and the associated precoding metrics are obviously affected by the scheduling decision. The choices of these parameters are mainly determined by the radio condition and the selected data rates, that is the transport block size. The scheduling decision is communicated to each of the scheduling terminal through the downlink L1 L2 control signaling using the PDCCH per downlink assignment. However, the overall goal of the most scheduler is to take the advantage of channel variations between the terminal and preferably to schedule transmission to a terminal when the channel conditions are advantageous. Most scheduling strategies therefore needs information about the channel condition at the terminal, buffer status and priority of different data flows, the interference situation in neighboring cells, if some form of interference condition is implemented there. The implementation specific scheduler strategy also takes care of the downlink intercell interference coordination. And a cell may coordinate with its neighbor cells the intention of transmit with a lower transmission power in the downlinks on a set of resource blocks. And finally, the neighboring cells leverages such information as the region of interference to schedule at cell edge or terminal that otherwise could not attain higher data rates due to the interference level. The second important one is the uplink scheduler. So the basic function of the uplink scheduler is similar to its downlink counterpart, namely to dynamically determine for each 1 millisecond interval which terminal are to transmit on which uplink resources. Please note that the LTE uplink is primarily based on the maintaining the orthogonality between the different uplink transmission, and the shared resources controlled by the E node B control scheduler is the time frequency resource units. In addition to assigning the time frequency resources to the terminal, the E node B scheduler is also responsible for controlling the transport format the terminal will use for each of the uplink component carriers. As the scheduler knows the transport format the terminal will use when it is transmitting, there is no need for outband control signaling from the terminal to the E node B. Scheduling grant it is valid for one subframe, which means that dynamically grants are valid for one subframe. That is, for each subframe in which the terminal is to transmit on the ULACH, the scheduler issue a new grant. Uplink component carriers are scheduled independently. If the terminal is to transmit simultaneously on multiple component carrier, multiple scheduling grants are needed. And then the valid UL grants are needed. Upon detection of a valid UL grant, the terminal will transmit at ULACH according to the information in the grant. This figure depicts the timing relation for the uplink grants. For the FDD, the grant timing is straightforward. An uplink grant is received in a subframe n, triggers the uplink grant and the uplink transmission in subframe n plus 4. However, for the TDD, the situation is a bit more complicated. The subframe n plus 4 may not be an uplink frame, and the TDD configuration is from 1 to 6. The timing relation is modified such that the uplink transmission occur at subframe n plus k, where k is the smallest value which is larger than or equal to 4, such as the n plus 4 here. This provides the same processing time for the terminal as in the FDD case, while minimizing the delay from the receipt of the uplink grant to the actual transmission. For the downlink case, note that this implies the time between the grant receipt and uplink transmission may differ between the different subframes. Furthermore, for the downlink heavy configuration, for example from 1 to 5, another property is that uplink scheduling grant can only be received in some part of the downlink subframes. Similarly, in the downlink case, the uplink scheduler can exploit information about the channel condition, buffer status, and priority of different data flows. And if some form of interference coordination is employed, then also the interference situation in the neighboring cells. The channel dependent scheduling, which is used for the downlink, can be used for the uplink as well. This figure shows the semi-persistent scheduling. In many situations, the overhead in terms of the control scheduling in the PDCCH is well motivated and relatively small compared to the payload on the DLSCH or uplink SCH. However, some services, most notably voice over IP, are characterized by regular occurring transmission of relatively small payloads. To reduce the control signaling overhead for those services, LTE provides a semi-persistent scheduling in addition to the dynamic scheduling. With the semi-persistent scheduling, the terminal is provided with the scheduling decision at the PDCCH together with the incident which is applied to every nth subframe until further notice. Hence, the control signaling is only once used and the overhead is reduced. The periodicity of semi-persistent scheduling, that is the value of n, is configured by the RRC signaling in advance, while the activation and deactivation is done by the PDCCH. For example, for VoIP or voice over IP, the scheduler can configure the periodicity of 20 milliseconds for the persistent scheduling, and once a task spur starts, the semi-persistent pattern is triggered by the PDCCH. Channel state reporting. A key feature of the LTE is selecting the downlink transmission configuration and related parameter depending on the instantaneous download channels condition. The channel state reports consist of one or several pieces of information. For example, the rank indicator. The rank indicator provides the information for the number of layers that should preferably be used for the downlink transmission to the terminal, or providing a recommendation on the transmission ring to use. It is reported by the terminal that are configured to be in one of the special multiplexing transmission modes. There is at most one RI reported valid across the full bandwidth, which means that the RI is frequency not select here. The other piece of information is the pre-coded matrix index, we also call it PMI. It is indicating which of the pre-coded matrix should preferably be used for the downlink transmission. The reported pre-coding matrix is determined by assuming the number of layers by the RI. The pre-coded recommendation may be frequency selective, implying that the terminal may recommend different pre-coder for different parts of the downlink spectrum. Furthermore, the network can restrict the set of the metrics from which the terminal should be recommended precoder, called codebook subset restriction, to avoid reporting precoders that are not useful in the antenna setup. Channel quality indicator, or we also call it the CQI. The reason to use the CQ is the feedback quantity instead of, for example, the signal to noise ratio, as they account for different receiver implementation in the terminal. It represents the highest MCS that, if used, would mean PDSCCH transmission were received in a block error rate of at most 10%. So a terminal delivering the data rate with more than 10% block probability when using the MCS indicated by the CQI would fail the test. Please note that the channel state reports are only recommended from the UE. The base station, on the other hand, is free to obey these recommendations or not. With regard to the pre-coded related recommendation, the network has two choices. One is from the UA to the E node B, where the network may follow the latest terminal recommendations, in which the E node B has to confirm that the pre-coded configuration recommendation by the terminal is used for the downlink transmission. On receiving such configuration, the terminal will use its recommended configuration when demodulating and decoding the corresponding DLSCH transmission. Since the PMI computed at the terminal can be frequency selective, and E node B when demodulating and decoding the corresponding DLSCH transmission, since the PMI is computed in the terminal can be frequency selective, as an E node B following the pre-coded matrix recommended by the terminal may have to imply different pre-coding matrices for different set of resource blocks. And the other one is done by the E node B itself. The network may select different pre-coded information about which then needs to be explicitly included in the downlink scheduling assignment. The terminal then uses the configuration when demodulating and decoding the DLSCH. And to reduce the amount of downlink signaling, only a signal pre-coded matrix can be signaled. It implying that if the network overrides the recommendation, then the pre-coding is frequency non-selective. The network may also choose override the transmission rank only, in which case the terminal assumes that a subset of the column in each recommended pre-coder matrix is used. Basically, there are two types of channel state reports in the LTE, aperiodic and periodic, which are different in terms of how a report is triggered. Aperiodic means that the channel state reports are delivered when explicitly requested by the network by means of channel state request, including in the uplink scheduling graphs. An aperiodic channel state information is always delivered using the PUSCH, that is, on a dynamically assigned resources. On the other hand, the periodic channel state reports are configured by the network to deliver with a certain periodicity, possibly as often as 2 milliseconds, on a semi-statically configured PUCCH resource. This topic is very important in the LTE, the interference mitigation and the avoidance. The biggest cause of the mobile network capacity is the interference. Interference is caused when the users of different neighbor cells attempts to use the same resource at the same time. Suppose that there are two cells that use the same frequency, for example 10 MHz at 1.8 GHz band, and each cell has a UE that uses the same frequency resources. As seen in this figure, if the two UEs are located at the center, for example A2 and B2, here no interference is caused. They use low power to communicate with the base stations. However, if they are at the edge like A1 and B1, their signaling can cause interference for each other because they use high power to communicate. Like all modern mobile communication technologies, LTE can be deployed with one cell frequency reuse. Fundamentally, this implies that the LTE transmission structure has been designed so that reliable transmission is possible for the low signal to interference ratio, which we call SIR, that may occur in a reuse one deployment when the same time frequency resource issues in the neighboring cells. Still, a one cell frequency reuse typically employs relatively large SIR variations over a cell area. As a consequence, the data rates that can be offered to the end user may also be varying substantially, with only relatively low data rates available at the cell edge. There are three approaches to mitigate the inter-cell interference. The first one is the inter-cell interference randomization. The next one is the inter-cell interference cancellation. And lastly, we have the inter-cell interference coordination or avoidance. So let me talk a little bit about the ICIC concept. ICIC or inter-cell interference coordination, it is defined in the 3GPP release 8 as an interference coordination technology used in the LTE systems. It reduces the inter-cell interference by having UEs at the same cell edge but belonging to different cells, and they use different frequency resources. Based on the station that support this feature can generate interference information for each frequency resource block and exchange this information with the neighboring base station through X2 messages. This form of messages, the neighboring base stations can learn the interference status of the neighbors and allocate the radio resources, for example, frequency, transmit power, etc., to their UEs in a way that would avoid the inter-cell interference. For instance, the UE belonging to cell A is using high transmit power at frequency F3 at the cell edge. With ICIC, cell B then allocates a different frequency resource, which is F2 in this case, at the cell edge, and F3 to its outer UE at the cell center, having the one at the center uses low transmitted power in the communication, which is one of the interference mitigation technique. Interference mitigation randomizes policy spreads the user transmission over a distributed set of subcarriers in order to randomize the interference scenario and achieve frequency diversity gain. Interference randomization policy sequentially allocates in each cell the user data over the time frequency chunks, and once all the requesting transmission have been allocated, a random subcarrier permutation is performed so that each user is randomly spread over the whole time frequency grid. The next technique is the intercell interference cancellation. The signal received from the base station is first estimated and then subtracted from the due to the orthogonal spread of data symbol and the resulting redundancy in the transmission. MCCDMA provides the possibility of iteratively removing the intercell interference at the receiver side without the need to perform a high complex channel decoding steps in the interference estimation loop. Therefore, the MCCDMA provides the means to perform the inter-cell interference cancellation at the price of a small amount of addition complexity. Basically, two approaches are proposed that differ in a way that inter-cell interference signal is estimated. The first one approach is called the hard inter-cell interference cancellation, which is based on the use of hard decisions of the demodulation. This approach is one of the simplest way of realizing interference cancellation. However, it is not efficiently applicable to OFDMA since the only source of the processing gain in this case is the channel coding present in the system, which is not exploited. And the second approach is called the soft intercell interference cancellation, which is based on the use of more reliable soft values provided by the decoding process. This approach requires a significant higher amount of complexity since a channel decoding step has to perform for each interferer. Interference cancellation can be also combined with the spatial processing when multiple antenna are present. In short, two spatial combining schemes are considered here. MRC, which stands for the maximum combining ratio, and also the IRC, which stands for the interference rejection combining, that can be implemented at the user terminal without implicating the transmitter. The next one is the intercell interference coordination or avoidance. So in intercell interference coordination, resource allocation is restricted through the coordination between the cells. The coordination of resources at each cell is achieved by the configuration of the common channel by the scheduling for the schedule-based channels such as the shared data channel. The intercell interference coordination restricts the time frequency resources that are available at the resource manager or the transmit power that can be applied at a certain time and frequency resources. The restriction on the allocation of resources or transmission power will provide the possibility for improvement of the received SINR and achieve the user throughput at the cell edge based on the corresponding time frequency resources in the neighboring cell. This figure illustrates an example of the coordination of the intercell interference. As shown in the figure, one cell frequency is reused at the center part of all the cells, whereas different band of frequency is used for the edge of the cells. This friction frequency reuse, which is introduced in the region near to the edge of the cell, is to avoid the interference from the other cells. The coordination between cells is mostly achieved by the scheduler at each cell site independently, not by the additional tight node B communication or additional UE measurement and reporting. In this case, certain intercommunication between the node base station will be required in order to reconfigure the schedule restrictions. There are two cases considered here. The first one is resource restrictions and the other one is the transmit power restrictions. So the resource restriction allocate different time frequency band resources to the neighboring cells. So each neighboring cell had different time and frequency resources. And the other one is the transmit power restrictions, which means that restriction on the transmit power that can be applied at certain time and frequency resources. Which means restriction on the transmit power that can be applied at certain time and frequency resources. Here are some interference coordination techniques shown in these three categories or these three cases. The first one is high data rate and limited spectrum allocations. Here one cell frequency is reused, so the same frequency is reused here, and then that frequency is also reused here. The benefit is that entire spectrum must be available in each cell. At the edges there will be a higher interference, as we can see that since they are using the same frequency, so the user at the edges, they will be highly influenced from the interference. Then in the other one, we have the reduced intercell interference with frequency reuse. So in this case, as you can see, we have different frequency reused at the distant cells. For example, this green, dark green is used here, but they are not adjacently used anywhere. Similarly, this one, the light green or the medium light green, it is used here, but this frequency is again not used in the adjacent cells. And the light green, the very light green, it is used here, but it is again not used adjacently. In this case, they can survive and they can uh, avoid the intercell interference. And then we have a third one case, which is adaptive reuse. And adaptive reuse, we are using single frequency at the cell center, which you can see the same yellow frequency is used here, and everywhere. At the center, it is the same frequency, but near the edges, the frequency is reused. For example, the green is not used anywhere in the neighbors, but it is used farther away, like here, and here. Similar cases for the light green, and then the bluish green, I think this one is also used farther away but not in the close. So in the edges the frequency is different, but at the center the frequency is similar, it is the same frequency. And these three techniques can be used for the interference coordination. For the uplink intercell interference, an E node B in a cell can use the information provided by E node B in the neighboring cells as an input. And for LTE, a number of such ICIC related X2 messages have been defined. One way to mitigate the interference is to use the power control at the cell users close to the borders, and that is to use less power to generate relatively, that is, use less transmit power to generate relatively less interference to the neighbor cells. Alternatively, to assist the uplink interference coordination, two messages are defined: highly interference indicator and the overload indicator. The highly interference indicator provides the information about the set of resource blocks within which an E node B is likely to schedule transmission from the cell edge terminal. That is, resource block on the neighbor cells can expect higher interference. In contrast to the HII, the overload indicator, or the OL, is reactive to the ICIC tool, essentially indicating at three levels, like low, medium, and high. For the downlink intercell interference, the relatively narrowband transmit power, which we call the RNTP, is defined to support the ICIC operation. The RNTP is similar to the HII that I just explained you here, in the sense that it provides information for each resource block, whether or not the relative transmit power of the resource block is to exceed a certain level. Now, another topic is the heterogeneous network deployment. In general, providing very high system capacity, traffic in terms of meter square, and very high per user data rates will require a densification of radio access networks. By increasing the number of cells at per meter square can increase without requiring the corresponding increase in the traffic that needs to be supported per network node. Also, by increasing the number of network nodes, the base station to terminal distance will in general be shorter, implying a link budget improvement and a correspondingly improvement in achievable data rates. A general densification of a macro layer, which is a high power cell with its antenna typically located at rooftop level, is reducing the coverage area of each cell and increasing the total number of macro cell sites. An alternative or complementary to the uniform densification of macro cell layer is to deploy the additional low power nodes under the coverage area of a macro cell. And such a heterogeneous or multi-layered network deployment, the underlaid picocell layer does not need to provide full area coverage. Rather, picocell sites can be deployed to increase the capacity and achieve data rates where needed. Another example of heterogeneous network deployment and the complementary of the so-called home eNode Bs are also referred to as femto base stations. A home eNode B or the femto base station correspond to a small low power base stations deployed by the end user, typically within the home or connecting to the operator networks using the end user wireline broadband connection. The femtocells are often associated with the closer subscriber group, with only users that are the member of CSG being allowed to access the home E node B are the femtocells. Thus, the users not being the member of CSG have to access the radio access network via the overlaid macrocells layer, even when they are in close proximity to the femtocells. So interlane interference may be more severe compared to the inter-cell interference in the same layer. For a wideband radio access technology, such as LTE, using different carrier frequencies for different cell layers may lead to an undesirable spectrum fragmentations. As an example, for an operator having excess of 20 MHz of spectrum, a static frequency separation between two layers would imply that the total available spectrum had to be divided with less than 20 MHz of spectrum being available in each layer. This could obviously reduce the maximum achievable data rates within each cell layer. Also, assign a substantial part of the overall available spectrum to a cell layer with relatively low traffic may lead to inefficient spectrum utilization. Thus, with a wide high data rate system such as LTE, it should preferably be possible to deploy multi-layer networks with the same spectrum available in the different cell layers. Cell selection could be based on estimation of the uplink path loss. In practice, this can be achieved by applying a cell-specific offset to the received power measurements used in the conventional cell selection, an offset that would compensate for the different cell and cell transmit. Such a cell selection strategy would extend the area in which the picocell is selected. It is therefore also sometimes referred to as the range extension. Selecting the cell in which the path loss is the smallest, this applying range extension will maximize the uplink received power or SNR, thus maximizing the achievable uplink data rates. Alternatively, for a given target received power and the terminal transmit power, this interference to other cells would be reduced, leading to higher overall uplink system efficiency. Also, it could allow for the system downlink physical resources to also be used in other picocells, thus also improving downlink system efficiency. Interference from the macro PDSCH transmission to the lower picocell PDSCH transmission can be handled by the scheduling coordination between the cells by the same principle as the inter-cell interference coordination within a layer. Interference on L1 L2 control scaling uh, like PDCCH, PCFICH, and PHICH can be dynamically scheduled. However, too low SIR, which is for example below the minus 15 dB, and a heterogeneous network with a range extended pico cannot be dynamically scheduled. So the solution for this is the carrier aggregation with the cross carrier scheduling. The protection subframe, the picocells use these frames for transmission to the user equipments in their high interference region. Signaling and protecting subframes patterns is supported by the eNode B of different cell layers. Here are some tips for the interference coordination in the femtocells. In the differences and limitations. So in case of the femtocell with the CSG, there are additional interference issues due to the fact that a terminal can be very close to the other femtocells and still have to communicate with the overlaid macrocells. Such a terminal may be very severely interfered on a downlink by any femtocell transmission and may cause even severe uplink interference in the femtocells. In principle, this can solve by the same means as above. That is by relying on the interference coordination between the scheduling and the femtocell layers and overlaid macro possibly extended by the carrier aggregation approach. However, a key difference in this case is the interference avoidance must be two-way. That is, one not only avoid the interference from the macrocell to the femtocell terminal in the higher interference outer region of the home E node B coverage area, but also the femtocell interference to the terminal close to the uh, femtocell, but not being part of the femtocell CSG. And the limitation is a further complicating factor in the home E node B scenario is that there are obvious limitations in the coordination between the home E node B and the overlaid macro layer due to the limited backhaul capabilities of the home E node B. And since there is no X2 interface to the femtocells, and in practice, the configuration of protected and non-protected subframe must be more or less static, something that could obviously affect the overall system efficiency. And here I will conclude my presentation, and I'm very thankful to all of you for having your attention. Thank you very much.